First of all, we would like to welcome today our guest and our collaborator, Honorary Professor of High School of Economics, Wila Aalst. Today we will have a ceremony related to honorary diploma of our university, and we will have a lecture by Professor Aalst. But our first speaker today is Vice Rector of our university, Maria Yurkevich.
Good afternoon, everybody. I was invited to say words about HEC and international labs, but it seems that you all know even better than me on what HEC is. We are quite young university. We are just a few years older than you are. So HEC is about 22 something, and you are 18, 19. So you are almost the same age, which means that I hope that you feel how HEC feels about itself. We feel young, we feel that the whole life is ahead, and that we can do anything, and we try to think big. That's why big data, which is a topic for today's speech, is very relevant for HEC case. And you probably know that HEC started as a very small economics-oriented master college. An idea was not to have humanities, not to have sociology, not to have computer science or mathematics, just to focus on economics. And here we are in 22 years. We have everything except medicine. We don't have medical clinics yet, but we probably should. And we don't have chemistry and biology. We have everything. And probably for us, 20 is a lucky number. Why? Because we are 22, as I said. We have about 20 buildings around Moscow, so we are a big dispersed university. And we also have about 20 international labs in HEC. Why international labs? As you probably know, HEC started with international teaching. Our first professors at HEC were not native Russians. Were people from all around the Europe, mainly from London School of Economics, from Erasmus University Rotterdam, and Sorbonne Paris 1. So there were people who came to us to help us to learn and teach better. So our first language of instruction was both English and French, and now we move toward Russian. So in a way we now come back to this tradition because we bring international scholars, the best international scholars in the countries, in the world, to teach us to grow further. And I think it's very important. That's why we create international labs. It allows you to work with the best people in the field. Not with the best people in Moscow or the best people in Russia, but just the best people from everywhere. Why is that? Because we want you to be the best people, not in Russia, but around the world itself. I think that's what our ambitions are. That's how our international labs work. We just bring simple the best people, both from students and from the international faculty, and that's how it works. So we now have about 24 international labs, and the lab, previously initially headed by Professor Aalst, is one of them. And we are very proud that in this very important, very fast-growing subject, we have such a group of young scholars. And we do look on this lab as a potential center which should go further and to contribute to our reputation in the future. Why 2020 is a lucky number for HEC? Because we also have honorary professors, and we have about 20 professors in HEC. So at this special occasion, we are to celebrate our 21st honorary professors. We're going to be our Professor Aalst. So I think that we are lucky in this way as well. So I don't think we should spend more time on speaking about HEC in general, but focus on their presentation and discussion. So I return the floor to Ivan.
Okay, thank you very much. So our next speaker for today's meeting is Professor Irina Almazova.
I would like to tell some words about Professor van der Aalst and about the research he's doing and his help to our research in the High School of Economics. And first of all, I would call Professor van der Aalst the inventor of process mining area in computer science. And so just it could be said that actually to pose a question is sometimes more important than to answer it. And to formulate the problem is extremely important in the research. And Professor van der Aalst was actually a person who formulated this problem of process mining. And the idea is that, of course, people were studying processes, modeling processes, analyzing processes, and it is very important in computer science because all information systems actually consist of processes, and sometimes they are very complicated, communicating, so interacting, so it is very difficult to understand sometimes how they behave in reality. So people understand that we need models and we need to analyze models to be sure that they behave in the correct way. But the new point was not to just to construct a model and then to use it to develop a software system, but to analyze the behavior of a real software system. Because, of course, there is a time gap between constructing a model and then developing a software system. And for instance, after some time, we can't be sure that the model is accurate, that it reflects the real behavior. So how can we use the information in event logs, which are held by all information systems? That's a very interesting question. And if it can help us to make process more correct, so just more efficient, then so that's great. And of course, it was a very good thing to pose this question, and of course, Professor van der Aalst did it, and then, so of course, he also has a team, and now this team actually is a net, a world net of process mining researchers who are studying this topic. Recently, there was organized a data center also in Eindhoven University, and Professor Wila van der Aalst is the director of this center. It is a new trend everywhere, and also here we have data science department, and so students have a new master program in data science, so it is very important. Of course, there are different aspects in data science. Sometimes it is how to find needed data or how to extract some information. But here in process mining, it is important that we deal with dynamics, not just static data. And so 2 years ago, a bit more than 2 years ago, Professor Wila van der Aalst helped us to establish research in process mining in Russia. So actually it was and still is the first center for process mining research in the High School of Economics, and we are proud of it. And we have very intensive international collaboration, and also I would like to. So you see that many people are already involved. These are students and staff members, and also some foreign staff members who took part in this research. And so we think that it is very important that young people should be involved in deliberations because in some sense, so just new ideas come with new generations. So we are to teach young students, and we are trying to involve students into our research, and we have some real success. So, for instance, 2 of our students so involved in laboratory research got prizes in research competition, student research competition, and also quite recently, a student who is working in the lab for already 2 years has got president stipendium, and it is given for research student activities. So it is very nice for all of us. And also, just now, so a team of students is on a conference for young researchers. It is a conference on software engineering, but for the second year, this conference has a special track on process mining. So we are advertising this research, and students help us with it. So this is about some results of our work. So we have, of course, papers, also with the students as well, and so everybody, you are welcome if you are interested. So you know that many students are working with us, both as staff members and just doing their postdoc or master thesis. Also, I would like to tell some words that Professor van der Aalst helped us with a master program. So we had for 5 years a joint master program with Eindhoven University of Technology, and Professor van der Aalst was giving a course on management of business processes, and it also helped us greatly. And also, I would like to add that now there is a course on Coursera on process mining. It is very popular. You can look at it and maybe take part in it to be familiar with this topic. Also, there were several talks in Moscow, so during visits of Professor van der Aalst about his topic young days at Moscow State University and some other places. And I think that all this gives a great contribution to the development of research, and actually that's what we are all working on. So it's a great pleasure now that we can dedicate Professor van der Aalst as a honorable professor at the Higher School of Economics. And of course, though formally, so he's not in the staff of our university, we continue joint research, and we hope that it will give new achievements.
Thank you very much. So we are ready for the first culmination of today's meeting. I would like to invite Professor van der Aalst, and we prepared an honorary diploma, and now we will start this. Are you ready?
Before I start talking about the questions and the passions that drive me, I would like to very much, first of all, thank the Higher School of Economics that they grant this honor to me. I would also like to thank the Department of Computer Science that they are supporting this. And of course, in particular, I would like to thank all the members of the Lab on Process-Aware Information Systems. Many are here. And a special thanks to Irina for driving this also when I was not here, that things were continuing. So thanks a lot. Some words were said at the beginning. I consider this to be also a great honor for the topic. I think when I started working on this 15 years ago, people were telling me you are completely nuts. This data is not there. You're thinking of things that are not possible. if we look at the relevance of big data and data science today, you can see that it was not such a stupid idea to do these types of things. So I think it's a great also honor for the topic itself. It's a topic of the future. And in terms of collaboration with this university, if I may want to give an advice, is that this university has a great potential. It is here in Moscow. If you see in let's say, a bit over 2 decades, it has grown to a university that is, I think, 3 or 4 times as large as my own university back in Eindhoven, which I think is a great achievement. There's also a research potential, but also, as was pointed out by the previous speakers, it is very important that young people are driving this. So it has to come from the young people, not so much hiring old professors from countries like the Netherlands, but stimulating young people to compete at an international level. It is very important if you do science, there are no political boundaries. You have to compete at a level. It doesn't matter where you do it, as long as you compete. So after these words, I would like to move to the topic of today. Let me switch this. So I will talk about the science of big data, in particular about process mining, so that people that are not familiar with the lab get a bit of a better idea what this is. But I would like to start very general, and I think everybody knows about big data. You hear about it in the newspapers, it's everywhere. We are collecting amazing amounts of data. So we are working with many companies. For example, one of the companies that is currently supporting 18 PhDs in the area of data science is a company called Philips, that you probably know from televisions and stuff like that. But they are very much targeting using data science to make their products better. So what they have is they have shaving devices connecting to the internet. They have baby drink bottles connecting to the internet. They have air purifiers that measure the air quality all around the world, are connected to an internet connection, and you can see what the air quality is at all these different parts, and you can see how people are using these devices. They have coffee machines that are connected to the internet, and that is showing that there will be large amounts of data that you need to analyze, and companies that are not exploiting this data, they will not survive, because they will not be as good as the companies that are exploiting this data. So we are generating data all the time. I see that my slides have changed a bit from one computer to another computer, so the animations have gone, but that's no problem. We are generating data all the time. So these are daily activities, and all these daily activities are leaving traces on human behavior or organizational behavior. Also, if you look at an iPhone, then if you look at such an iPhone, you will see that it has many sensors, and these sensors, they are also collecting events. So in general, I'd like to talk about something that I call the Internet of Events. What we are doing as humans, what devices are doing, what all kinds of other things are doing, we are constantly generating events. And the question is, how can you collect these events and analyze them in a meaningful way? As I said, it's not helping me that the animations have been gone, but I think everybody knows Moore's law, that every 2 years the number of transistors on a chip will double. If you look at Moore's law, this applies to everything. Right? It applies to the number of pixels in a screen, the capacity of a hard disk, 1 divided by the cost of 1 megabyte storage. So all of these things are growing. So this is a straight line on a logarithmic diagram. So it is showing that this is going incredibly rapid. So 15 years ago, as I said, people were saying there is no data. If you look at us, what kind of data we are generating today, it is incredible what we are generating, and there is no reason to think that this will stop. So if you look at big data types of things. There are typically the 4 V's. There is the V of volume, large amounts of data. There is the V of velocity, and that is that data is coming in so fast that you can no longer store, or you don't have like large amounts of time to think what you're going to do with this data. You need to do something immediately because of the incredible speed. Also, processes are changing while you are analyzing them. Twitter behavior today can be completely different from the Twitter behavior tomorrow. So there is no point in saying 1 year later you should have done something different like 1 year ago. It doesn't work. Variety, you need to kind of merge data from very different sources. So there can be structured data, but there can also be free text data. There can be images, and somehow you need to merge all of these things into a single question and analysis problem. And last but not least is veracity, and that means that what you are seeing is not necessarily completely correct. The example that I like to use, Philips knows that it has sold me a shaving device. If the shaving device is connected to the internet and my son is using it, then Philips may think that I'm shaving myself. So there is always this uncertainty in data that you need to be able to cope with. So there is a need for data scientists. If you look at the salaries of a data scientist are incredibly good. If you look at the demand of the data scientists, that is also growing. At this point in time, we are also involved in a large European project where we look at the education of the data scientists of the future. So making MOOCs and all kinds of other things. If you look at a company like Philips that I mentioned before, they are saying that they are hiring between 60 and 80 people per year of data science experts. So compare that to how many software engineers they are hiring. That is already comparable, and in the future I expect that there is a much bigger need for data scientists than software engineers in a particular area. So a data scientist should be able to collect, analyze, and interpret data from a variety of sources, and I already talked a bit about the sources of information that I'm referring to. So it's about turning data into value. So, as I said, I'm trying to emphasize in the initial part of my talk the fact that this is a new job. And it's a very important job. And people will be screaming for people having this expertise simply by the following reasoning, that in 2 years' time there will be again, I don't know, numbers differ between 2 to 10 times as much data. So who are the people that will somehow interpret this data? There is an incredible need for people that are able to do this. So if I look at history, and this is a bit based on the Dutch setting, but I'm quite sure that it is comparable, mathematics has been taught in universities forever, right? It has always been there. If you look at computer science, I come from Eindhoven, and I was the first professor in computer science that actually studied computer science. So all the professors before me, there were people that had a degree in physics or a degree in mathematics. Nobody had a degree in computer science. You also, for example, if you look at this time just before here, there were people in Eindhoven like Dijkstra, the person who invented the shortest path algorithm that you probably know. These were real mathematicians shifting to the area of computer science. So Dijkstra, these people were typically teaching courses just at the beginning of this. They were mathematicians, kind of with an orientation towards computer science. So why was there suddenly this explosion? So in Eindhoven, and I'm quite sure it's here, we educate much more computer scientists than we educate mathematicians. I think the ratio is, I don't know, 1 to 4 or something like that. For every mathematician, We are educating 4 computer scientists. So this area has become really big. So why was that the case? The answer was very simple. Here, there were already computers before, but this was the point in time where suddenly the use and the availability of computers started to explode. It's a similar situation as what we see now, that now suddenly there is so much data. Data was always there, but now suddenly it is coming in such large amounts that we need to deal with them in a more systematic way. So this is creating this area of data science, which is much more than mathematics and computer science. Some people define data science as the intersection of mathematics and computer science, which I think is missing the point a bit. A data scientist should be able to turn data into value. So people also need to know things about ethical things, privacy, business models, and stuff like that. So in Dutch we have a saying, I'm not sure whether it also exists in Russian. You are basically looking for a sheep with 5 legs. Is it also a saying in Russian or not? So in Dutch, when you look for somebody that has many capabilities that are very difficult to combine in a single person, it is said that you're looking for a sheep with 5 legs. Like you're looking for something that is very difficult to get. And the same is the case if you look at the data scientist. Because if it's just like a pure mathematician or a pure computer scientist sitting in a room making calculations, you will not be able to turn this data into value. So you also need to have people that appreciate the human aspects, the business aspects, and also think about the processes that are behind this data. It is not just looking at the data. So if we define what the competences are of a data scientist, then we typically show this flower. And let me walk through all of these different ingredients, and then you can see that we are indeed looking for sheep with 5 legs. So first of all, of course, the basics people should be good at statistics and stochastics. It's kind of amazing that all around the world, statistics groups were subcritical a couple of years ago. They didn't have enough students. And now suddenly there is a huge demand for the capabilities, but they have been focusing too much on it from a theoretical perspective, not thinking about kind of these other domains that I will discuss in a minute. So for example, in statistics, people have been focusing on the problem, what to do if you have very little data, and if you have very little data, can you still make a reliable conclusion? Now, if you look at the time of data science, it's not that you have very little data, it's more the problem that you have a lot of data. In fact, you can see everything. And that requires a different perspective. Then, of course, there is the area of data mining and machine learning. So data mining originates from the area of statistics. But in the early days, data mining was like a curse word. If you would say to somebody, he's a data miner, you would mean something negative. Somebody that is trying to draw conclusions that are not scientifically valid. If you see what has happened today, this has become an area that is much more important than some of these classical areas. Then there is the area of process mining. Data mining is typically focused just on static data. Process mining is focusing on the processes that are actually generating the data, and that's what I will talk about more later. Then, of course, you need to be able to deal with large amounts of data that require a particular infrastructure. So if you think of things like Hadoop, MapReduce, special types of databases like the database underneath SAP, the HANA database, these are these new technologies that allow you to scale at the scale of Google or at the scale of Yandex. That you need to have these types of things. Then there is visualization. That is one of my favorite topics where I think there is a lot of value in that. And to illustrate this, I brought a few pictures with me. And now, of course, the animation, because the animations are gone, it's not working. So what you could see here are 4 data sets which have an x coordinate and a y coordinate. And each of these data sets consists of 11 points. if I would look at the average value on the x-axis, all of these 4 data sets are exactly the same. If I would look at the average value on the y-axis, all of the average of all of these points are exactly the same. If I would look at the variance, so the distribution over this y dimension, all 4 data sets are identical, the same holds for the x-axis. If I apply linear regression, then all of these 4 data sets generate exactly the same linear function, this blue line that you see here. Yet they are completely different. Now as a human, you look at this data and you immediately see these data sets are different. So somehow, these automatic techniques are often not enough if we are looking at a problem that is not structured well enough yet. To illustrate this a bit, this is something that has been developed at our university. It is a tool to visualize the content of your hard disk. So the colors indicate what kind of type of data. So if you look at this and you are using this tool, you will immediately see, is my hard disk now occupied by movies, by system files, by text files, by audio, and you see it in one glance. And I would not know what kind of table format to show that would show this amount of information. Note that your directory structure is visualized in here. Another example, which is of course very appropriate talking in Moscow, is that this is one of the earliest applications of visual analytics. So this is the march of Napoleon's army to Moscow, and the width is indicating the number of soldiers, and this is the retreat. So you can see that in the end, just a fraction of the soldiers survived. And it's one picture that is containing a lot of information that would be very difficult to capture in a rule or in a table or something like that. A more recent one is, this is a visualization made by one of our students. It is visualizing that you can see what has happened in a football game in one glance. And for the people that like soccer, they may remember the game, of course I picked my examples, of Spain against the Netherlands last year, which we won 5-1. And you can see the goals being scored here. But this line is based on an analysis of the movements and the actions of all the players. So there are cameras above the field. They analyze how players are moving, what are the things that are happening, and it is indicating which team is in the lead. And here, so we Dutch, we think that, well, we had a glorious victory and we were much stronger, but if you look at the actual analytics, you can see that there were times that the Spanish team was much stronger. So it's again, how to visualize data from very low level to a level where people can actually understand this. Because this is based on a player is moving from that XY point to that XY point, etc. Then to stay in terms of soccer, you of course also need domain knowledge, somebody like the Dutch coach. What is very important is behavioral and social sciences. Probably that is less of an issue here, but at this point in time, you can see that lots of Dutch organizations are, on the one hand, applying data science heavily. On the other hand, they are a bit afraid of applying data science because they are afraid how the public will react to it. So if the public finds out that you're using data in a way that is not completely accurate, this can lead to incredible effects, even a company going bankrupt if they don't do this properly. So privacy and security are very important topics. Of course, industrial engineering, in the end somebody has to pay for this. Now that I'm showing this picture, for example, so just to see the breadth of data science, you can all imagine if you think about Yandex, if you think about Facebook, if you think about a large bank, if you think about, I don't know, the government, you can all imagine that they have lots of data. But there are also lots of data in places where you don't expect them. So for example, we are working together with a company called Van der Lande. they are making these conveyor belts that you see at many airports. So if you fly to Schiphol, your luggage is being handled by this system. They track exactly where every suitcase is going. So if a suitcase moves from one place to another place, this is exactly tracked. Also, they have incredible amounts of data available. Also very important from a security point of view, that if a luggage turns up at some place, how did that luggage get there? And was it really justified? And of course, now we have completed the circle, database and algorithms are also important. So this is showing that data science requires input from many disciplines. At this point in time, I'm involved in a jury at the national level where we are collecting what are the scientific questions that science should look at in the next couple of years. And we have asked the Dutch citizens what they think is important. And if we ask them, then you can see that many of the questions that the Dutch society is asking from science is how to deal with these large amounts of data. On the one hand, how to put them to use. So how to make medicine better, how to make transportation better, etc., etc. But at the same time also from concerns. Are these techniques being used in the right way? So from that, I have collected some questions, some high-level questions that may be interesting for you to look at. So one question is how to extract value from data without stopping time. That is a kind of a deep statement. It says that if you are looking at many applications, you have to be able to react immediately. If you are shopping online, you cannot say, oh, I should have advised the customer to look at this advertisement. No, you need to do it immediately. And you have to realize that things are changing. There is a drift. So you have to react immediately. And what was happening yesterday is not necessarily representative for today. So you cannot stop time and then do some analysis. You need to do it in a different way. Another interesting question is related to discrimination-aware analysis. How to avoid unfair conclusions even if they are true. And let me explain this. If you apply data mining and you, for example, need to make the decision, am I going to give somebody a mortgage or not? Then I can look at their credit history and all kinds of things. And then, of course, it would be very unfair if we would say we give a mortgage to males and not to females. Or we would say we give a mortgage to white people and not to black people. That would be completely unacceptable to do something like this. So what you do then is that from these data sets, you remove, is it a male or a female? You remove, is it a black person or a white person, etc. You remove everything that you don't want to use. And then you build, for example, a decision tree. And it may be that that decision tree, although you have left out these variables, is now using other variables that correlate strongly with these types of things. So it may be that you've been politically correct, but you're still making the same conclusions. So sometimes you want to force algorithms to be fair. That's, I think, also for the acceptance of this technology, it's very important. Another kind of deeper question is how to answer questions that were never posed. As was said at the beginning also by Irina. Often asking the right question is answering the question. But if you look at a large amount of data, what are the questions that you should ask? Perhaps you know the statement of Rumsfeld. So we often focus on the known knowns, the things that we know that we know. The known unknowns, and even better, the unknown unknowns, these are the things that are more interesting to look at. What do we not? We do not know certain things, and we do not know that we don't know them. But still they are very important. And And that's kind of the data science mindset that one should have. How to answer questions without revealing secrets. So we once had a data set from the largest Dutch pension fund, and we got a dump of all the millions of people, and one of my employees took 1 minute to find himself, just by combining different types of data. So if you give an analysis result, you want to make sure that people cannot reveal things about people that you don't want to be known. Who should decide? Data or the expert? So is it, should we go for automatic techniques, or should we go for expert knowledge? The last question, I think everybody knows what correlation is, but correlation doesn't necessarily mean that there is also an implication. So things happen together, but there may be a third variable that is influencing this. And that is, of course, in a time of big data, that is something that is very dangerous. Kind of people can easily misuse these types of things. So the question is how to detect these things. What you see is that many of these questions are not new. They are questions that have been there before, but they have become extremely relevant because of the things that are happening in society. So typically, as you can take it one level higher, what is data science about? It's about things in the past, like what has happened, why did it happen, but it also talks about the future, what will happen, and what is the best that can happen. These are the generic questions that you would like to answer. After this very high-level introduction, I would like to talk more about process mining, and I have the feeling that with the animations this is not going to work very well, but let's try. So what is process mining? After explaining you this entire flower, process mining is the connection between data science and things that are related to processes. So you can think about business process management, business process re-engineering, but also formal methods, model checking, concurrency, Petri nets, BPMN diagrams, UML activity diagrams, state charts, sequence diagrams, whatever. This is about behavior of processes. This is about analyzing data. And process mining is the bridge between these two areas. I hope that you can see that that is why this is very, very important. If you analyze the data without knowing about the processes, you cannot add much value. So this is exactly the topic of what is being investigated in the lab in process-aware information systems, not studying processes without looking at the data, looking at the combination of processes and data. And that's a very timely topic. So this, I think, is the part that will go wrong now. So if you look at the relationship between data and processes, you can view this in multiple ways. And one way to view it is to think of process models like this playing out behavior. And as I said, that there would have been an animation walking through this process model. So it would see that you first start with a registered travel request, then you have an OR join, then you split here things. You always check the budget. You sometimes do these types of things. And that leaves an audit trail like this. So given a process model, you can automatically, you play out this model and you see a trail. So people that are using SAP or that are using the information system from the university, in the background there is some kind of process, hard-coded in Java or in models or whatever. And when you use the system, you generate this type of behavior. You can see what activities have happened at what time by which people. And here you can see another run, but you cannot see it, but it would be another trace. So given one such model, there are many behaviors that you can generate from it. Yeah? So this is going from a model to an event log. Now we are going to shift it, then we get into the topic of data science. Now we don't have the model, we are interested in the model, But we have lots of data. We have, for example, all the student records of any student that ever studied at this university. And now we would like to analyze study behavior. How can we automatically construct these types of models? And that is where, let's say, process discovery and process mining comes in. The metaphor that I'm always using is the metaphor of a desire line. So this is my youngest daughter, Loesje van der Aalst. And she is showing this is the official path, but my daughter and everybody else is really doing this. So this is what is happening if you would look at the university systems and you would see what people actually do and what they say they do, and you look at the evidence, you will see all kinds of shortcuts. So are these shortcuts bad? Not necessarily. This is just showing that the path should not have been here, the path should have been here. So that's how you try to use data science. In terms of process discovery, this means that you start with a bunch of examples. Think of this as students that followed a particular curriculum, and you automatically construct a curriculum. Or you look at patients that have been treated in a hospital with a particular disease. You know exactly what has happened to these patients, and then you automatically construct this model. That's the idea. So given these traces, you can automatically infer this model. As I said, it's a bit a pity that the animations are not working, then that would be a bit more clear. So there's no modeling needed. You just take the data and you automatically generate this. Here you see this on a real-life data set. So you take a bunch of events, you automatically construct this model, and here you can zoom into part of this model. So I could take a look at your study behavior, I could take a look at your Twitter behavior, your Facebook behavior, and I could construct models. How do people typically behave, or how do organizations typically behave? Not in terms of a decision tree or something static, but in terms of a process model. Then there is the important topic of replay. So the idea of replay is that you have a model. So you're not trying to discover a model, you have a model, and you try to highlight in the model and in your data where do things deviate from reality. So here you have a process model, it's in Chinese. It is saying don't walk over the grass. That's like a model. And if you look at the evidence, then you can see that people are walking over this over the grass. So you see that there is a problem. Here you see this was a system designed very safely to avoid people from cycling in the path, but you do conformance checking and you can see exactly where people deviate. So that's what conformance checking is about, finding these deviations. And because of the animation, there is a bit of a problem here. So if I would replay this one, I would see no problems. This trace, this behavior, fits into this process model. If I take a look at this trace, then if you analyze this trace correctly, you will see that this D activity, checking of the budget, is missing. It never happened. So I can highlight in the model that there is a problem at this place. People are deviating there. Here I can see another example trace where you can see that there is both an acceptance and a rejection at the same time. So I can also highlight that in terms of my model. So I can do this for this replay. I can do this also with time. Then I can see if I look at the process, I can see how much time was being spent in all of the different parts of my process. So if I would look at student data, I would see, okay, students typically get delayed because they fail to do this course, they do it again, and then it takes a very long time. So these types of information I can plot for one student, but I could also plot it for many students, and then I get an indication where are the bottlenecks that we're looking at. So to summarize, we have play out. You start from a model and you generate behavior. That is when you program a system. That is basically what you're doing. But it's much more interesting at this time where you have lots of data to start from the data and to automatically discover process models or to automatically check conformance between a process model and an event log. So there is software to do this, and people from the lab here are also contributing to this. There's a software PROM that is providing close to 1,000 different plugins. You should think of 1,000 different analysis techniques that you can use to tackle data. It is very confusing for people to use because of the complexity. So when people use it, it feels a bit like this. You have all this power, but if you want to just open a wine bottle, it's a bit overkill. But this is what research is about. Research is trying to find out what are the good knives and what are the good tools that people need in practice to turn data into value. There are also many commercial tools based on the ideas that we have developed. Some of them have been founded by former students of mine, so for example Disco, and also the software that is being used here. They are much simpler, but they are as simple as using a spreadsheet. They're very, very easy. So let me say a few words to go one level deeper, and then I will come to a conclusion. How does this discovery part now work? Because I tell you all of these beautiful things, and I didn't explain you any algorithm. I just said it's magic, and then you get it. But let's go on this particular topic, and as I said, there are 1,000 different types of analysis that you can do, but just that you get a bit of an idea. So first, it's important to realize that the data that we are talking about is everywhere. So what you see here in this table are exam grades. So a particular student takes a particular course and gets a particular mark on a particular day. So if we look at this data, this is event data. Every row corresponds to an event. There is something like what we call the case ID. And so the process is about a student, the life cycle of a student. We have an activity name, in this case it's making the exam, and we have a timestamp that is indicating when it has happened. So to do process mining, you always need a case ID, an activity name, and a timestamp. If one of these things is missing, you cannot do it, but it's everywhere, this type of information. So back in Eindhoven, we are not just analyzing student performance at exams. We are also looking at several online things, like analyzing these online courses. Most of our lectures are available on video, and then we can analyze how did people use these videos. We are actually now generating reports that teachers can look at, and they can see what is now the relation between my students watching particular lectures and getting certain exam results. Another example, and we just completed a book on this, it's analyzing processes in hospitals. So if you look at a hospital, the data is very nice because any record in a hospital refers to a patient. So it's very easy to kind of correlate these different data elements, even if they are scattered around hundreds of tables. So we can see events, they refer always to a patient. There can be an activity like a blood test or surgery or something else. We have a timestamp. There may be the doctor or the nurse that has done it, and we may have all kinds of other information. Again, what is mandatory are these first three columns. So it's very little, and you can do these things. Last example is order information, like you can find in any information system of a company. We have order numbers. We have activities like check stock, ship order, handle payment, stuff like that. And we have timing information. So this is the kind of data that we need, and I hope that you can see it is everywhere. If you now look at the basic discovery problem, then we can now filter out many things. We can use them later. For example, if you want to know where are the bottlenecks, who are responsible for certain problems. Then we start looking at this other data. But first we would like to know what is the control flow. What are the sequences of activities that people do? Well, if you do that, then it is not important, for example, what the exact order number is. You just need to know which events belong together. It's also not important to know what is the exact timestamp. You just need to know the ordering of events. The timestamp itself is not relevant. We also don't need this data. We just need to look at the activity name. Activities are connected to cases, and we know which things belong together, and they have a particular order. So what we get is data that looks like this. So for example, this is a case where we first had register order, check stock, ship order, handle payment. And that's one execution of this process. And this is the kind of data that we take as input. So let me briefly show you this, so how you can convert this data into a process model by looking at this simple event log. And now it becomes a bit more abstract. I've renamed these real names to things like A, B, C, D. But here there was a case where we had a sequence A, B, D, E, F. So this could be one student taking this course, this course, this course, this course, this course. Or it could be one patient that first had a blood test, then an X-ray, then surgery. So sequences of events. And we try to convert them into a process model. So there are many ways in which you can do that. What we are trying to do here is we try to split the labels, so A, B, C, D, into two sets in such a way that these labels have a clear relationship. And now if you take a look at the data, you can see that I can, if I look at the activities A, B, C, D, and I look at the activities E, F, G, then we always see these ones followed by these ones, but we never see these ones followed by these ones. There is never an E followed by an A. So if I can split my set of activities in two sets, and things from one set may be followed by things from the other set, but not the other way around, then I know that I can split my log based on this. So if I do that, then these traces are cut up in this part A, B, C, D, and this part E, F, G. And then this is what I get. So if you look at this trace, then you can see I can reconstruct it by taking this trace followed by this trace. And I did it by analyzing here, are there things just jumping from here to there and never the other way around? So it's a very simple rule. And note that this can be done at the scale of Google, because we just need to take one pass through the log. We are basically just counting, so I can distribute this over as many computers as I would like. It's incredible. The things that I'm talking about, you can do, they are just limited by storage space and the number of processors that you have. Now I try to repeat this trick that I just did, and you can see that A is followed by these other things, but never the other way around. So I can again split it in this. Now what more can I do? I hope that you can see I can do here, I see E versus F and G. I do again this. So I'm taking the log and I'm making the log smaller and smaller, into smaller parts. Now I cannot apply this sequence rule anymore, but now I can look, are there logs that I can cut like this, where I can see that there are traces where just one set of activities appears, versus traces where the complement, the other set of activities appears. If that is the case, then I don't have the sequence operator, but I have the choice operator. So please carefully take a look at this column here, F and G. You can see that I can split it in F and G in such a way that in traces either just one set or the other set appears. And I can kind of decompose this into two logs with the XOR operator. So are there more of these things that we can do? We can focus on this column. And what you can see is that we can split this into B and C and D, not in the sequence or the XOR operator, but with the AND operator. And I'm skipping some of the details here. But I hope that you can see that that is like the sequence, but the order is not fixed. Right? That's the idea. So I can parse this log into this. Now there is just one column that is not atomic, that is this one, with B and C. And again, this is an XOR. And now I have reduced my original log to a set of smaller logs that all talk about just one label. And now if I look at how I did this, then I get this tree. And it's a bit difficult for you to see. But you can see I started with this big log, and I reduced it to logs where just one activity was appearing. And if I now read back this diagram, I can see what the construction of the process is. So here I show it in terms of a Petri net. Here I show it in terms of a BPMN diagram. So what we find based on this technique is that it always starts with an A. After A, we always do a D, but there is a choice between B and C. And B and C, this B or this C can happen before or after this D. They are not in a particular sequence. So we have concurrency. Then after doing D together with a B or a C, we can do an E. And after E, we do a choice between F and G. And that's exactly the behavior that we saw at the beginning. So this is an example of one of these many techniques that you can apply. It is incredibly scalable. So you can scale this at the scale of Google, let's say it like this. And some things that I didn't show you, it is also very robust to things like noise. So you can filter out infrequent behavior if you would like. This is a kind of a screenshot of the tool. I plan to give a demo, but I'm skipping that. So to come to a conclusion, I would like to thank for this great honor. I hope that for the people that were not familiar with this field of data science, that I hope that our world is driven by data. Data is everywhere. And of course, if you start doing this, then people will complain, well, but my company is not recording that, or we record that, but it's not always true. That is the same people that said 3 years ago that the iPad would never be used, and it's everywhere. That all these developments that we see are very recent. So we are driven by data, so that should have implications on people having an interest in mathematics and computer science. You need to kind of use this new reality. There's an incredible need for data scientists that will continue to grow in the coming years. I stress the point that it is not just about static data. It is very important that you see that data are generated by a process. It's like also the goal of a company is never to have a good database. The goal of a company is to have a good process. That's something that's very important to bear in mind. Process mining is bridging this gap between these process-related topics and these more data science-related topics. It is very different from business intelligence. And so skeptical people will say, well, this is like business intelligence. And so what is business intelligence doing? Business intelligence is showing you pie charts and tables. That is not rocket science. That's not the solution. It's like if your child has fever, that you measure what is the fever that this child has. That's simple spreadsheet stuff. If you do process mining or data science in general, you have to do better than that. You need to put in some smartness, some intelligence in there. So you can view process mining more like taking an X-ray. You're not looking, does the child have fever? No, you're looking, let's say, inside the child. What are all the problems that you see if you look at the level of the real events that have happened, rather than just measuring fever? And so if I go to a company, and the company says, well, we have problems with our flow time, we want to do things in 2 weeks and we take 1 month, they don't need to hire a data scientist to measure that they are taking too long. They need to have a data scientist to look inside the process to see what they can improve. And that's exactly what process mining, let's say, tries to do. Taking this data from the inside of the process and understanding what is really happening. Irina already referred to the MOOC a bit before. So we had the first run, and there were 43,000 people kind of that participated in the MOOC. That's why we very quickly did another run that was just finished. It was just finished, I think, a week ago, where 25,000 people joined. I think it's still open if you would kind of look at it today, but it will be closed very soon. There will be another run of this course again later this year. It's also very interesting from an educational perspective to see how the dynamics of teaching are changing. Like, rather than standing in front of a room with, I don't know, 50 or 100 people, there is this potential of, let's say, learning at a larger scale. Of course, we are also applying process mining to the data that is being generated by the students to see what things they find difficult, where do they stop watching, what is the relationship between errors that they make at the exam and things that they watch or did not watch. These are the things that we look at. Thank you very much for your attention, and thanks again for this nice ceremony.
Are there any questions or comments?
Just going back to your university time, I mean, when you was a student, you said you studied computer science as maybe in the first.
Yeah.
What you done as a student work? I just want to learn your origins, because what you did for the student work and what were the steps to the data science?
Okay.
Your steps.
Yeah,
Your
so-
steps, please.
So if I look, as I said, I was studying computer science in the second year it was given. So in the second year given, I would say it was a bit experimental. So the things that I remember is that there were lots of still physics in the program, which I found very strange, because I've never used any of it later. What was also very clear is that at that point in time, it was not so clear what the curriculum in computer science should be. So I was in Eindhoven. There were many people involved in proving the correctness of programs. So I got many courses like, around the weakest liberal precondition and things that people do not get today anymore, I think, about proving the correctness of a program or deriving a program. That's what the emphasis had. Then if you look at my scientific career, from origin, I'm a PetriNet researcher. So I'm looking at formal methods, modeling processes. We have been doing that for many years. That was also how I got into the area of workflow management, let's say 20 years ago, to 25 years ago. From this PetriNet, I naturally moved into the workflow management area. But then I saw that organizations have big problems of putting these process models into software in such a way that people actually start using these systems. Because you can see that you can make a description of this is the process, but first of all, there is a big gap of turning this process model into actual software. And then this actual software was typically quite unrelated to what people wanted to have. And like during the implementation process, you often need to revise completely your ideas on what the software should do. So then, I would say in the late 90s, I felt that this is a bit stupid. We are, as scientists, we are proving things about the correctness of models, and of models where we know that they have nothing to do with anything in reality. So that drove me, let's say, into this area. So then with this strong theoretical background, let's say concurrency, etc., we started to look at how to relate data to this process, and that was the start of the area. And as I said in the beginning, many people were against it, and they were also saying that we were completely stupid in doing so. I still remember the first case studies that we did. What was the data? The data was that people would write on a piece of paper when they started to do an activity and then when they were done. These were our event logs that we were using in the beginning. It now sounds absurd, but it's like you will find many things in 10 years absurd that you think now as being very advanced. Yeah, so that's a bit of history.
Any more questions? If not, then let us hope that Professor Aalst will continue to visit us regularly, and thank you very much for your attention.
Thank you.